Okay. Thank you. And thank you for attending the last lecture of my lecture series. So today I'm going to talk about the GUI method applied to the Euler equation. This is in the outer GUI scheme. So let's record in the previous four lectures. In the lecture one, we discussed the initial GUI, the finite dimensional reduction. In the second lecture, we discussed infinite dimensional reduction for concentration on high dimensional sets. And in the last two lectures, I discussed the parametric GUI, the L2 case, and the non-L2 case, which we discussed last time, dimension 2, 3, 4. And so today I will discuss the GUI method applied to fluid equations, in particular the Euler equation. So Euler equation is the best well-known fluid equation. So it's given in the velocity is u dot gradient u plus gradient v equals 0, and incompressible. Right? This is so I'm going to discuss in 2D. I'm going to discuss how we use GUI method to establish the dynamical correspondence, and in the 3D, I will discuss how we can use the GUI method to give a rigorous construction of the Leaf-Flogan phenomena for the 3D Euler. Right? So let's start with 2D Euler. Okay, so the 2D Euler in a bounded domain, we have this in terms of velocity, it's ut plus u dot gradient, and u equals the pressure, and this low flux boundary condition, and incompressible, and the initial condition. So omega is a smooth and bounded domain in R2 or the entire space. So this problem, if you look carefully, so this problem here, we don't see second order derivative. So we only see first order derivative. And in fact, if you consider this u as a fixed function, this is nothing but a transport equation. So this is a transport equation. So, and what I want to show you is how we can apply the GUI method for this transport equation, So first, we studied the so-called vorticity stream function form. So if you take omega as the vorticity, which is gradient times u, and psi as the stream function, so u is the velocity. So in terms of the stream function and the vorticity, this equation is very simple. And it becomes just a transport equation for the vorticity. But this transport term depend on the vorticity by this Poisson equation. So here we see the Laplace. Equation. So, and I'm going to work with this problem, and we're going to show how we can do the GUI for this problem. So the steady state for this Euler equation in the vorticity stream function form, the steady state is this equation. So this equation says the along the level set of psi, and the omega should be constant. So this is the first equation. And second equation, we have the Poisson equation. So if the vorticity is a function of the stream function, then of course, then this satisfies the first equation. And so this means then we have this, the gradient per psi times gradient omega equals 0. So any solution, okay, for the semi-linear problem is a solution is a state state for the Euler. And not only this, any regional symmetric function is also a steady state. And there are also many other state states, like the one-dimensional case, And so there are there are very rich results for the local well-posedness and well-posedness. And the best result for the 2D case is Udorich, and he showed that if omega 0 is L infinity, then you get a global existence and uniqueness. And if omega 0 is regular, of course, you get regular all the time. Now, this seems to the best well-posed this result. If you relax L, W0, L infinity to LP, you can also improve the existence of some measure valued functions. And there are many results on vortex wave system and so on. And recently, there are also, in the last 10 years, there are many using the contour integral convex integration technique. There are many constructions on many compact supported weak solutions to the Euler equation. And we will not discuss this because this is a huge field, okay? So I'm trying to discuss, what I want to discuss is the relation between this Euler equation and the nonlinear PDE and the semi-linear problems. So we consider solution with a Dirac form. Suppose omega, the vorticity, is highly concentrated at a finite number of poles. For example, we can say that formally assume that the vorticity is a sum of finite many Dirac measures. Okay, then under the Euler flow, the motion of the center of this vorticity will follow the so-called Kirchhoff rules dynamics, and this has been formally derived by Helmholtz, Kirchhoff rules, and Cécilin. So suppose we have the vorticity is just sum of Dirac measure. So of course the stream function are nothing but the Green's function. And this is the definition of the Green's function. So Green's function can be decomposed into Newtonian potential and the regular part. Right? This is the Green's function. So now formally, if we have a sum of Dirac measure, we can compute that omega t is the gradient of a Dirac measure times zeta j prime, and this convection term, this gradient per psi gradient omega, you can put formally. You get this is the Green's function, and this is the gradient Dirac, and you get this type of because Green's function is gamma minus h. H is the regular part. This is the singular part. And since both gamma and the Dirac are regionally symmetric, so these two terms becomes this inner product of these two terms becomes 0. And so we only get this term. So what we get is formal computation. This is a formal computation. We get K prime. So we have the K prime here, and we get the gradient pep of this function and times gradient Dirac. Now this is a well-known function in when we do concentration. This is called the Kirchhoff rules, reduced energy function. So for this is a formal derivation. If we have a Dirac measure, and then formally, then this location trajectory will solve the following Hamiltonian system. This Hamiltonian system is called Kirchhoff rules system. Okay, the Hamiltonian system. So this is a non-rigorous derivation. Okay, and so the dynamic correspondence for 2D Euler is the following. Suppose we have a solution for the Hamiltonian system, for the Kirchhoff rules Hamiltonian system from 0 to capital T. Can we find a family of true and smooth solutions to the Euler system so that the vorticity in the limit, single limit approach to the singular to the Dirac measure, okay, and on this trajectory. So this is the so-called desynchronization of vortices. Okay, this is called the dynamic correspondence for 2D Euler. Okay, so how to find a true solution for the Euler equation? Okay, so if we assume that we have a steady state for the Kirchhoff rules, so these are critical points of the Kirchhoff rules function, then we can do elliptic construction. So a good model is the Newell, or this is a semi-linear type. This is also a very useful semi-linear type, which is u minus 1 and to the power p. So we can use both this kind of nonlinear terms, and we know the results from the elliptic green. We know that if you have non-degenerate or topologically non-trivial critical points, then we can have a steady state for this problem or this problem, which concentrate on this Kasai. And this has been done in many elliptic papers, right? Many elliptic papers, and with e to the u, this Brackett and Packard and Grossi Pistoia, Despino, Krosik and Musso, and with this u minus 1 to the p and Cow and many people. But what we are concerned today is not the elliptic problem. So the elliptic problem is you start with a non-degenerate critical point of the Kirchhoff rules, you construct a steady state for this nonlinear problem, which is also stated for the Euler. And what we are concerned today is the dynamic problem. And suppose the Kirchhoff rules Hamiltonian system has a dynamics, and from 0 to t, and can we find a solution to the Euler, true solution to the Euler with the concentration on this trajectory? So this is what we want is not a elliptic problem. It's a dynamic problem. Okay, it's a dynamic problem, and the answer is yes. And there are some results, previous results, and material and performance, and they assume that this vorticity has compact support, and they prove that in some L1, they prove that they construct a solution, but in L1, okay, in L1 convergence. And our purpose is to give a rigorous construction of this dynamic correspondence. And moreover, we want to find the fine structure. Our solution, the vorticity will be no longer compact support. And we also want to find the fine structure, even the next order in this construction. So more precisely, we found solution of this form where precise ipsum is precise zero ipsum and plus little precise ipsum, and this and with this Poisson equation and omega zero ipsum precise zero ipsum, the explicit ipsum recognition in this of this Dirac measures, and we choose is the solution is like a Green's function, almost like a Green's function. We choose this recognition for the stream function, and so that the vorticity is like this, and this here we use the new will, and in the limit we get this Dirac measure, and here we use the solution to the new will to do the construction. And so our main result is very simple. Assume that we have a smooth and coordinationless solution for the Hamiltonian system from 0 to capital T in some finite time. Then we have a solution to the 2D Euler, and the solution to the Euler, 2D Euler, will look like the following. So the vorticity will be like 1 over epsilon squared times U0. The U0 is given by this e to the gamma 0 by the new will, and the psi is a solution to the new will, almost a solution to the new will, and we have precise point-wise estimate for the remaining terms. So this is a work with Juan Davina and Depina and Monica Musso. We call the Green method for the vortex dynamics in the Euler flow. And here we gave a rigorous construction for this dynamic correspondence. So basically our result says as long as you have a solution to the Kirchhoff-Roos Hamiltonian system in some finite time, then you have a solution to the Euler whose vorticity is like a Dirac, and like Dirac, and we can also have precise point-wise estimate in the remaining terms. So this is this gives a definite answer to the dynamical correspondence. Okay, so we prove this by the Green method. Okay, so what is new for the Euler equation? So the new ingredients in the construction for the Euler equation. First, we have to improve the approximate solution in powers of epsilon using elliptic and transport equation. So and up to very high order, and then we set up the problem as a coupled system of inner problems near the singularity and the outer problem near the away from the singularity. Now, the problem for the Euler equation is the outer problem is are transport equation. And for transport equation, we don't expect to gain any regularity. And this is the main problem. So the inner problem is also a transport equation, but you can treat it as an elliptic problem. But the outer problem is another transport equation. And so how do we do the decoupling, the inner outer? So in this case, yeah, unlike the elliptic case or the parabolic case, we have to treat the outer problem very carefully because we don't gain regularity for the outer problems. And we use a priori estimates to solve the problem. We use the result and we by continuation the degree argument and not by conjecture mapping. So the new ingredients for the growing for the Euler. First, the inner problem is highly degenerate. Okay, and as we're going to see, there are lots of kernels for the inner problem. And the second, for the outer problem is a transport equation, and we don't gain regularity. So both inner problem and outer problem are transport equation, but the outer problem is only log epsilon better than the transport equation than the inner problem. So this is this is the key. Even though the transport equation we don't gain regularity, but we can still use some kind of improvement of regularity to distinguish the inner problem and the outer problem. Okay, so let me show you how to improve the approximate solution. So this is our the Euler equation. Okay, this is like S of u, right? This is like S of u. So this is a non-local because this is a minus percent equals omega, and we look for approximate solution like this. Okay, percent 0 and plus y and omega is u0 plus phi, and percent 0 is like the indefinite case, right? This is like e to the u, and so in terms of the rescaled variable, the first error you plug in this, okay, you plug in this. The first error you're going to get is the following. So you're going to get gradient. You're going to get a cassette dot, okay, because we'll compute omega t. You're going to get a cassette dot here, and you're going to get gradient per percent 0 and gradient per psi. Okay, now we decompose the elliptic part, and we know that near the singularity, the percent string function will be like gamma 0. Gamma 0 is a solution for the new wheel, and so because this is the Kirchhoff rules, and we assume the Kirchhoff rules dynamics, so we'll get this equals so this equals gradient per gamma 0 plus r. R is small, but this guy has a singularity because this one is like a log r. Gamma 0 is like a log r. So the first error is like this, and by direct computation, we say that the first error will be like epsilon square order, okay, and then we have to find the next order. So we use a reduction in the error by solving the problem, the linearized problem in this way. And so in terms of the polar coordinate, the linearized problem, forget about the T, is like a third order. So the this linearized operator is like 1 over 1 plus rho squared d over d theta of a second order. So this is like a third order equation. So if we look at this linearized problem, if we look at this linearized operator, and what we see is very interesting, but very challenging. This operator is highly degenerate. It's a third order, and all radial functions are in the kernel. So you don't, and so in addition, you have this is the linearization of the Liouville that we discussed last time. And for the Liouville, you will have 3 kernels, right? You have the scaling and the 2 translations. So in terms of the linearized problem for the Euler, we have now a huge problem with the kernel because all radial functions are in the kernel. This is a huge problem. And in addition to these 3 kernels, okay, to these 3 kernels. So if we want to solve this problem, use this L and to solve the error here. And we need this error to be a function to be able to write as d over d theta. So this error here cannot have any radial component. If you have a radial component, you cannot use this part to solve. Okay? And fortunately, in the first error we don't have a radial component, and so we can still solve. We should get a mode 2 and 3, and we can improve. And so we get the next order will be epsilon to the 4. Okay? And but this is not good enough. And the reason is the following: because the mode 0, you can one order you can use the radial part, is the OD part, and for the OD part you lose epsilon square. So then, and to get a good error and a fast decay, we have to solve this problem. We have to use the OD part. You cannot just use this one now, because if you use this one, if you have a mode 0 radial symmetry part, you are in big trouble. Okay, so we have to pick up this phi t term. So in the end, we need to solve this kind of transport equation with this type of right-hand side. Okay, and if we can solve this type of transport equation with this kind of right-hand side, and we plug in, we get a new error which has fast. We have epsilon. We have smaller epsilon to power 5. We have decay. Okay. So this is I explained to you what is the problem with the linearize. If you linearize around the vortex, the problem, and this is the linearized operator around the vortex, and the main problem here, our main enemy here is that this linearized operator, which is third order, and cannot solve any error which is radial symmetric, because it's d over d theta of something. Okay, So all radial functions are in the kernel. Okay? And to solve the radial function, we have to use this phi t. We have to use phi t and use the transport equation. So this is the transport equation we need to solve. Okay. Okay. So now I'll show you what is the inner and the outer GUI. So this is our first answers, and we write the problem, the vorticity as eta j. So we have like k Dirac, okay, k concentrations, and each of these will do a cutoff, and then we have this inner function and phi j, and then we have this outer function, the outer, okay, and this is the for the stream function. This is the inner, and this is the outer. Okay, so want to solve this using the inner outer GUI. And so what is the equation for phi j and phi out? Okay, so phi j and phi out to solve the following system. Okay, and phi j for the inner solves this problem here with the singularity. This gradient pipe gamma 0 is a singularity because gamma 0 is like log r. So this one is like 1 over r. Okay, this one is a big singularity. Okay, so the inner problem takes care of the singularity. Okay, takes care of the singularity. Now, what is the outer problem? So outer problem is a transport equation. Okay, but the coefficient in front of transport equation is better. It's given by this, and this one has smoothness. Okay, this coefficient has a smoothness. So, and of course we also have these cutoff functions, just like the parabolic GUI or the elliptic GUI. We have the outer to inner to outer, and the outer to inner. We have this type of couple. So both equations, the inner equation and the outer equation, they are transport equations. Okay, but the inner problem, for the inner problem, we put the singularity, the most single part of the transport term in the inner part, and for the outer part, we solve a transport equation with less singular coefficient. Okay, and so this is the inner and the outer GUI scheme. So we solve this system by a continuation degree argument, and so now we need to solve the inner problem. So the inner problem is a transport equation, is I couple the transport equation with the elliptic third order elliptic equation. So this is the inner problem we need to solve. We need to get some kind of RPL estimates for the inner problem. Okay, so the outer problem, this is the equation for the outer problem. Okay, and for the outer problem, we show that using the transport equation, we show that the solution actually we can get a better like C1 control for phi. Okay, and here we use the captivates function, and we just using the captivates curves, and we can write down the solution explicitly, and simply we use the captivates equation, and we can estimate this phi directly. Okay, and it turns out that we get a little bit more regularity for the outer problem. So I will not discuss this estimate. So the main problem now is the inner problem. Is how we solve this transport equation with I third order term here, elliptic part, and how we solve this equation. So this equation we can write in terms of the polar coordinate is epsilon square phi t plus 1 over 1 plus y squared d theta of this. And as we see that if this part has a radial part, has a multi-zero part, we cannot use this one to solve. We have to use this one to solve. And if we use this one to solve, we're going to lose epsilon square. Okay. But in general, we don't want to lose epsilon square. So this is the inner part, and we need to design a theory to solve this inner equation. So how to solve this inner equation? How to get estimate? Okay. So as in the elliptic problem and the parabolic problem, this is the most important part, is to get, first you show the existence for this for the inner problem, and second you show uphill estimate. You need to have a good estimate for this inner problem, because with this only with a good estimate for the inner problem, your inner and outer going can work. Okay. So this is the problem we need to solve now. So let's look at the unique part. Okay, this is the unique part. So this unique part is d over d theta Laplace psi plus f prime of gamma 0 and psi. As I said, this problem is this operator is highly degenerate because all radial functions are in kernel, and you also have 3 additional kernels. So how to solve this problem, this transport equation, and we're going to solve this problem using energy method. So the natural way to measure the size of the error and the solution is to this norm, E square and U0 minus 1. And with this norm, the right-hand side, our error we get is epsilon to the 5. So essential gradient is a L2 uphill estimate that involves both the elliptic and the time derivative at the same time. So a simplified version of the K estimate is as follows. So this is the uphill estimate. Suppose phi solves this transport equation. And we assume that phi is orthogonal to the translations and the rotation, the scaling, right? This is the scaling. And then we have this L2 estimate. And you lose epsilon square, okay? Because of the epsilon square. But we still get L2 estimate. We get the L2 estimate. So you see that this L2 estimate is like, suppose I don't have this in the middle. Suppose I don't have this. So this L2 estimate will be like, basically like OD. You can treat this problem as OD. But here we have this elliptic part. So how to deal with this? So this elliptic part gives us a log epsilon, okay? And how to prove this? We prove this by a good test function. So this is our test function. Our test function is phi over u0 and minus phi. And if we test this function here, this operator with this test function, then this operator here will become this, and because since u comes on the user region symmetric, we get this, and it turns out that this term here, okay, disappeared because you have the radial, you have this integration by parts. Okay, and so using the orthogonal condition, so we get, if we multiply this function by g, we get the estimate for phi g. But we want to get estimate for L2 estimate. So now we need a Poincaré inequality, which says the phi g can bound phi square. And so it turns out this Poincaré inequality, we can prove this Poincaré inequality by moving everything here by the stereographic projection, and it turns out this phi g is in the stereographic projection is phi tilde minus 2 times lambda phi tilde, and though using the Fourier expansion, and you get, because of the orthogonality condition, and you can have a spectrum decomposition of phi times g, and because your phi is orthogonal to the first two, the translation and the scaling and the rotate and the scaling, and so phi is orthogonal to the first eigenfunction, first eigenvalue. So your lambda j starts actually from 4. Okay, starts from 4. So this will be a positive number, and from this we get the Poincaré estimate. Okay, so we lose some log. Now, this type of estimate, we also found the application of this type of Poincaré inequality when we studied the Kender cycle, the bluff for the Kender cycle. The bluff for the Kender cycle, the linearization, the parabolic going, precisely we use this estimate. Okay, where we have this type of estimate. So once we have this energy estimate, and this gives us L2, but to get LP, we multiply by phi p minus 2 and phi, and use the transport. And unfortunately, we don't have a cancellation, so we have a loss of boundary terms, and we're going to get the LP estimate, and so by interpolation. And so this gives us the energy estimate. So let me just, the most important thing for the inner problem is this L2 estimate, energy estimate for this transport equation. And with this L2 energy estimate for the transport equation, then we can get a global estimate. So as long as your phi is orthogonal to translation and the scaling, and we get the L2 estimate. And so the proof, we use the spectrum analysis. So this finishes the 2D case, and to cap. So the proof of this, the result we prove is a dynamical correspondence. So if we have a Hamiltonian system in some time trajectory from 0 to capital T, and we're able to construct a solution to the Euler system which follow this trajectory, and we prove this by the in-outer going, and the most important difficult part is this operator which has too many kernels. Okay, all real functions in the kernel. So, and to get the estimate, we use the energy to get the estimate for the inner problem, and we use the energy method, and we test this with different functions, and we get this energy estimate. So once we have this, then we can now do the inner outer grid. So this is the whole idea. The even if you have a transport equation, we can still use the inner and the outer grid. So this is the 2D case. In the remaining part of my time, I will discuss the 3D order, which is more difficult. So in the 3D case, the 3D order, if we write in the stream function and the vorticity, the problem becomes the well-known the Werner equation. So omega t equals u dot gradient omega minus omega dot gradient u. So now the problem is that this is a transport equation, but this one is a stretching term. So in the 2D Werner, you don't have this term, but in 3D Werner, you have this term, and we have to deal with this term, and we have this minus Laplace psi equals omega, and u is the velocity. U is the velocity. So what is the problem we want to consider in 3D for 3D Werner? So the 3D Werner, now we want to construct a solution so that the vorticity is concentrated not on points, because the vorticity now is a factor. So the vorticity is concentrated on some curve. Okay? So in a Epsilon neighborhood of a curve, this is called a filament. Okay? Vortex filament. And they are parameterized by gamma. So this is called the vortex filament conjecture. So can we construct a solution to the 3D Werner which concentrates on a curve, not on points, okay? Concentrate on curve. So this is like the smoke ring. And this is called a vortex filament or binomial flow conjecture. So, okay, so in the 2D case, our solution is because the stream vorticity and the stream function are scalar. So we consider Dirac, right? Dirac at the points and concentration at the points. In the 3D case, we consider concentration on a curve, okay? Like this. So this is a nearly singular solution for the Werner. So, just like a 2D case, what is the dynamics for this filament? Now, in the 2D case, the dynamics for the points is the Kirchhoff-Roos dynamic law. So what is the dynamics for a curve? Okay, and this is called a binomial flow. So if we consider a tube along the curve, and you use the free-net framework, right? Free-net framework. So you have a normal direction and a binomial direction, and you have the tangent direction, and we have the free-net formula, okay? And in a neighborhood of the curve, we can introduce the Fermi coordinate, and so we look for approximate, just like in the 2D case, we look for approximate solution for the 3D Werner flow, and with this, so along the curve is like a concentration along the curve, and we still use this Wei function. We still want to use this Wei function as the concentration, as the concentration. Now it turns out because of the curvature, you have to correct the Wei function by some curvature, by the kappa. And this is because of the Laplace term, okay? And so you plug in this one into the Euler equation. So suppose we have this, and we plug this into the Euler equation, and you do some computation. This is again, this is a formal computation, and what you found is this binomial flow. You found that this curve must evolve by the binomial flow, and this is called the binomial flow equation. Binomial flow for the curve, and this has been put. Okay, this has been derived by Nefer Shvita and lots of other people, but by all different methods. Okay, so this is the vortex phenomenon conjecture, or the dynamic correspondence for 3D. Dynamic correspondence 3D or Euler. So given a solution to the binomial flow, so we have shown that if you have a concentration on a vortex on the filament curve, the curve should follow the binomial flow. And we ask the converse question, the dynamical correspondence. So given a solution to the binomial flow, can we find a true solution to 3D Euler flow such that the true solution to the 3D Euler will be a smooth solution, but as the epsilon goes to 0, maybe the smooth solution will approach to a Dirac on the curve. So this is called the binomial flow conjecture, the dynamic correspondence for 3D Euler. And there are some evidence of proof by Gerard and Sayes, and they show that if the vorticity are concentrated and around the tube, and under some technical conjectures, conditions, and this will evolve in weakness to the binomial flow. Now, this conjecture is unknown and is still completely open, except some special cases. Okay. So, what are the examples of binomial flow? First, we have this helix is a binomial flow. So helix is a binomial flow with constant angular speed, rotates at a constant angular speed, and this is one binomial flow. Another binomial flow is vortex ring. Okay, is the ring, the vortex ring, the traveling ring. Now I will discuss this in one moment. Let me first discuss the helix. So the helix is a known example of binomial flow. You can write down the helix explicitly. Okay, and for helix we can prove this binomial flow conjecture for the finite complex, because we can construct a global solution to give a helix. We can construct a global solution to 3D Euler, and the concentration follows the helix, and you can also do multiple helix. And this idea here is very simple. So you can also do double helix. The idea is to reduce this problem to elliptic. And it turns out the problem that can be reduced if you have a helical symmetry. The problem can be reduced to an anisotropic semi-linear problem in R2, and using the Green method for the elliptic problem, we can group a concentrated solution for this, and this solution will be a concentrated solution along the helix. So in some sense, this is a cheating because you reduce this problem to the elliptic problem. Right? So and the second class of binomial flow is vortex ring, and this is the one I'm going to consider next. So vortex ring is a well-known example of binomial flow that does not change form. Okay, and it traveled vertically with a constant speed alpha, 2 of r. Now, solution to Euler equation with vorticity concentrated around traveling circles, and this is called a vortex ring. And this solution has already been constructed. So let me show you. So since we're doing the vortex ring, so it's better to consider axially symmetry using some symmetry. So you consider axially symmetric Euler, and then the 3D Euler will become a two system, 2x2 system. So you have U1 and W, and here we see that the stretching term. This is the stretching term. This side, this is the stretching term. Now, if we assume that the swell, this is called swell, if we assume that there's no swell, and the 3D Euler becomes almost like a 2D Euler, but with this some inhomogeneous terms here, okay? Some inhomogeneous, and here the Laplace is not in Laplace in R3 or R2, it's a 5-dimensional Laplace, and this is because of the change of 5. And for this problem, Poincaré in 1972 found the exact traveling ring solution for this problem. And you just simply reduce this problem to a semi-linear problem. And you found a solution for this semi-linear problem. And with this kind of inhomogeneous terms. Okay? And so let me now explain the construction of Poincaré's ring solution by Green method. So you take this, suppose you have a concentration at some r, okay, and you expand the Green's function, and you take your famous the Newell potential. You assume you have a Newell potential, and you plug in the answers in, and you compute the error, and this is you get the error. And the error, you want the error to be orthogonal to the kernel, and the error orthogonal to the kernel, and give you exactly the speed. So you can use the initial green to get the vortex ring solution, traveling vortex ring solution. So the speed is 2 over r0. Okay? But of course, there are many variational constructions. But here is this analytical construction. So the speed is like 1 of r. So if the radius is small, then this travels fast. If radius is big, then it travels slow. Okay. So and there are many other traveling ring solutions. Multiple traveling ring solution we also discuss with Weaver Au and Yong, and this is related to Eidner-Moser polynomials, and you have 3 traveling rings, right? And you can multiple 13 traveling rings. So I will not discuss this because all this is a lot of these are the integral theory. So in the final part I want to discuss is what if we have 2 parallel rings and they are very close, and what is the dynamics? And this is called Helmholtz conjecture. So when two force rings interact, the Helmholtz in 1985 he conjectured that if we have 2 ring, okay, vortex ring, they travel in the same direction, and they will mutually affect each other, because since in addition to proper motion, if they have the same direction, they travel in the same direction, and the front one widens, so become large, and slower, so the radius become large, and then the speed was slower, and the one behind radius become small, so it travels faster. since the speed is like 1 over the radius. So what happens is called a leapfrog phenomenon. So you take two rings, and the front ring become larger, and so travel smaller. The this ring travels faster. So this one move this. Now, if this one move ahead, then you will become smaller, then become larger, and then travel slower, and this one will become really become smaller, will travel faster. And so this is like a leapfrog, right? This is the leapfrog. So the question is, can we get a rigorous proof of this leapfrog for the order 3D order? Okay, and this is the next theorem I'm going to state. I'm going to use the GUI method to prove this. So we want to mathematically justify the leapfrog dynamics for the 3D axially symmetric order flow without a swirl. So this is the 3D order flow without a swirl, and so let's now take two rings, okay, Frank range solutions, and the vorticity will look like this, okay, and we do computation. So to describe the local dynamics, and we expand the variable, and we compute, and we're going to say that the error you're going to see that the error you have, that this is the vorticity of the ring, the P1, and it carries a log, and this is the interaction from the two different rings, and this is the capture term. This is the capture term, and so now if we assume that the size of the distance between the ring is like 1 over square root epsilon, log epsilon here, then you get you can from this dynamics, and you can get a reduced dynamics. It's called a leapfrog. It's a leapfrog dynamics, and this is the formal derivation of this leapfrogging phenomenon. So this leapfrogging dynamics is a Hamiltonian system, just like the Kirchhoff rules is a Hamiltonian and the system, and you can in the two vortex ring case, the leapfrogging dynamics is you can get all the trajectory, okay? Get all the trajectory for the leapfrogging. So you see that inside here, you see some kind of periodic solutions for the leapfrogging, and this is exactly this vortex ring. This leapfrogging, you see some kind of periodic structure because going out, going in, and going out, and going in. So this is the formal derivation, and this is the leapfrogging dynamics, and this is the trajectory. Okay, now just like a 2D case, we have derived the leapfrogging dynamics. Okay, we have derived the formal leapfrog dynamics, and the question is, can we rigorously prove the leapfrogging? And the answer is yes, and this is a recent work with Juan Davila and Depino and Musso. And our result says the following: if you have a conditionless solution for the leapfrog dynamics, which is this one, the leapfrog dynamics, suppose up to some time t, there's no collision. Okay, so B1 and the B2 they don't collide. Okay, if there's no collision, then we found I solution. Okay, to 3D axially symmetric ordinary flow without a swell of this type. Okay, and here the PJ, which has the vortex rotation, and they're given by this dynamics, by the Neufroger dynamics, and we can also compute the stream function. So we give a rigorous proof of the Neufroger phenomena, at least in short time. Okay, as long as there's no collision, we can have a rigorous construction of this concentrated dynamics. So what is new about this phenomena, about this problem? What's new about this problem is we're going to see 4 different scales about the problem. First, we're going to see Epson order. So this is around the vortex ring. The vortex ring, the tube will be like a Epson order. Okay, so this is the inner scaling. And then the distance between the vortex ring is 1/log. Okay, so this is a second scale. Then there's a larger scale, which is order 1. So we see 3 scales at this. But we should see another scale, which is 1/log. Because within 1/log, you will have a traveling rings. Okay, this is the traveling ring solution. The within 1/log, you see steady states. You see traveling rings. So you're going to see. So we see 4 different scales for this problem, and we use the inner outer going and for the Euler equation to prove the theorem, and so we need to improve the approximate solution in the power of Epson, and we're setting up the problem as a coupled system inner and outer, and then we do the inner outer going. So first, let's try to improve the error. Okay, improve the Epson. So we take this is our operator. This is our operator, and we take a counter function like this. So, and this is the 1/log scaling that in this structure here, and so in the most inner part is order Epson order, but then in the intermediate part you have 1/log Epson, and the distance between the 2 vortex rings is 1/square root log Epson. So you see 4 different scales in this picture here. Epson order, 1/log Epson, 1/square root log Epson, and order 1. So this is a multiple scaling, and which one is the inner problem? Which one is the outer problem? This is the inner problem. This is the one we're going to use as the inner problem. So we cut this, the inner problem, up to 1/log Epson. And the rest of this we're going to take as outer problem. Okay? Rest of this as outer problem. So we put this inner and outer, okay, and we plug this one, and so this system becomes the inner outer, and so you plug in the error, and because of the extra term R square here, you're gonna see some extra like a Epson order here, and so here to improve the error, So we have the inner error and the outer error, and we have this L2 estimate. This as we discussed before. Okay, and so the whole construction, we need to get an approximate solution to with this Epsilon 5 over rho cube. This is error. This is like the 2D case. And how to improve the approximation? And the improvement approximation, okay, so this is very complicated. So let me just show you. These are the 10 steps to get the last error. Okay, so these are the 10 improvement. The 10 you go from E0 to E1 and to E2 to E3 and to E4. So sometimes you use the ODE, sometimes you use the elliptic, and you use the ODE again, and use the elliptic, and use the transport equation. And in 10 steps, you're gonna arrive at this error. Now, once you have this error here, then you can use the L2, use this L2 theory. You can use this L2 theory and to close the loop. So this is a more complicated version, but for the problem with us, well, we can still solve. Okay. Some remarks. There's another mathematical justification of the leaf program by Gerard and Smith, but for the GP. And so our growing approach we develop and will be useful in the vortex filament conjecture. And this is one of the open, okay, questions, well-known questions for 3D Warner is the vortex filament conjecture. And this is we hope that we can use this green approach to solve this vortex filament conjecture. And the problem is for the vortex filament conjecture, you can improve the error, but the problem is you don't have the L2 estimate. Okay, the estimate was just like we had for the inner problem. This is the difficult part. So this is the final slide. This is still very much open, the vortex filament conjecture. And so given a solution to the binomial flow in a short time from 0 to capital T, can we find a true solution to the true 3D Euler flow which concentrate along this curve? Okay, this is vortex filament, the dynamic correspondence for the 3D Euler. And there are two recent papers on this, one by Fontanos and Vega, and they discuss with some viscosity term. So with for the Navier-Stokes, they discuss the evolution of the Fischer's vortex filament and desynchronization of Biot sub integral. And a very recent paper by Garnet and Spivak, and they take the Navier-Stokes equation, but with concentration on one ring, okay, and just on one ring, the axially symmetric ring, and they consider the dynamics of this under the Navier-Stokes equation, and this paper appeared in 2024. Okay, this is the end of my last lecture on the green method, and this is a new adventure to apply the green method to Euler problems, to fluid equations. and which is completely different from the elliptic and the parabolic. And hopefully, this green procedure may be applied to many other different problems, for example, like geometric flow problems, like and in other like even maybe Navier-Stokes. This is this this will be a dream for if we can solve the construct a finite time block for the Navier-Stokes using the green, and this will be the homework for the young people in the audience. Thank you.